All right, we're still on exam 4. This is on the review. It's part 4, and we're on problem 10, problem K, letter K. Now, if you look at K, it's got the 3 stars there. This is a challenging problem. We didn't cover this in class, so you probably want to skip this one, but I will do it here. So first of all, we take the log of each side. That's something that we haven't done before, but it certainly, basically I'm taking the log base 10 of each side. And just like with so many things that we do to each side, whether we're multiplying each side by 2 or taking the square root of both sides, as long as we do the same thing to both sides, we're okay. Now the next thing we want to do here is use the power rule and move those exponents out front. And so I'll do that on each side. And so we have the log of 6 times x plus 1. I'm going to distribute there, and I get x log of 6 plus the log of 6. And I'm going to do the same thing on the other side. Now the problem here is we've got 2 x terms. Since I'm solving for x, I want to get those 2 terms on the same side. And the log 6 and the log of 4, minus log 4, I want to get those on the same side. So I'm going to basically rearrange the equation so that that's the case, so that I have that. So I basically added log 4 to both sides, and I subtracted x log of 6 to both sides, and so I get what I have here. So once I've done that, now I can factor out an x on the right side. So I'm going to go ahead and do that. And so finally, to get x by itself, I need to divide by that large expression 2 log of 4 minus log of 6. And so finally, I get log of 6 plus log of 4 divided by 2 log of 4 minus log of 6. Be careful when you put that in your calculator. You'd want to enter or press enter after you put the numerator in, and put your denominator in parentheses. And if you do that correctly, you should get 3.2402. So again, that's a more challenging problem than any of the ones we did in class. Alright, so I want to talk about our approach for solving logarithmic equations. So it's actually quite similar to what we did with exponential functions. So one of our strategies is we just switch forms. And so we can change from a logarithmic form to exponential form. The other strategy, basically if we have 2 logs that are equal and they're both with the same base, then these inner numbers, m and n, must be equal as well. It's similar to what we were doing with exponential functions. If we had the same base and we had 2 exponential functions that are expressions that were equal, then the exponents had to be equal. So with logs, these inner parts, m and n must be equal if these 2 logs are going to be equal. So I like to say we have equal parts. So let's go, and you'll see how we do that when we get to one like that. So on number 1 here, or sorry, letter L here, I'm going to put this down here. When we change forms, we get 4 to the 3rd power equals x. Certainly it's not the second case where we have log equals log. On the right side we actually have a number 3, and so all we could do here is switch forms. And notice how simple this is now. This is just 64. So easy to check this, right? We could just plug in 64 and you can see log base 4 of 64 does equal 3. Certainly if we wrote it in exponential form, we would have 4 cubed equals 64. So anyway, that does check. Let's move on to m. So again, I don't have log equals log, so I'm not using the second strategy. We're going to switch forms again. So we have a base of 3 to the 4th power equals 3x minus 5. Of course, 3 to the 4th is 81. And this is a simple equation at this point. We're going to get 86 thirds, or 86 over 3. And to check this, we could plug that 86 over 3 in. Let's see, 3 times 86 over 3, that's just 86. Minus 5 is 81. And it is true that log base 3 of 81 equals 4, because 3 to the 4th power is 81. Alright, so let's move on to n here. Now notice this time we have 2 logs on the left side. Now we learned these properties of logs, and this was the main reason. We had a product rule, and here we have a sum of logs, and so that's what we're going to use so that we can have just one log. So I'm going to add that to our strategy for logarithmic equations. If there's 2 logs on the same side, we want to use the product or quotient rule to condense the log, or to condense into one log. So that's what I'm going to do here on n. I'm going to make one log out of this using the product rule. A sum of logs can be written as a log of the product. So we get the log of x times x minus 21 is equal to 2. Of course, our base is 10 here. So let's go ahead and switch forms. It's base exponent answer. We're going to get 10 to the 2nd power equals x times x minus 21. I'm going to go ahead and distribute there. That's x squared minus 21x. And of course 10 squared is 100. Now this is a quadratic equation, so I want to get 0 on one side and everything else on the other, so let's do that. And I'm going to move up here. So I need 2 numbers that multiply to negative 100 and add to negative 21. And without too much trouble, you should be able to find that 4 and negative 25 work. So this factors as x plus 4 times x minus 25. And so we get negative 4 and 25. Now, here's where we have to think a little bit about our answers, because one of the reasons why I've been checking my answers with these logarithmic equations is because I need to. Because we know that we can't take the log of 0 or a negative number. Notice here, if I plug in negative 4, I don't even care about the other part of the equation. I can't take the log of negative 4 because I can't take the log of a negative number or 0. And so this negative 4 is not going to check. Now if we plug in the 25, this becomes the log of 25 plus the log of 4 equals 2. And we can use the product rule, and it'll be the log of 25 times 4, or the log of 100 equals 2. And that is true because my base is 10. 10 squared is 100. And so the 25 does check, and so that's my only answer. So with logarithmic equations, the big thing we got to watch out for is that we don't take the log of a negative. If we find ourselves taking the log of a negative, we're going to have to throw that answer out. But again, we should always check our answers to make sure that they work. Let's go ahead and move on to the next problem. Now letter O is a little bit different than any of the ones that we've run into in our work. Notice we do have a log on both sides, but the problem is that 1. I can't get it to just be log equals log. And so the only thing I could really do here is get rid of that minus log 3 of x plus 5, log base 3 of x plus 5 on the right side. I'm going to add log base 3 of x plus 5 to both sides. And so now I get log base 3 of x plus 3 plus the log base 3 of x plus 5 is equal to 1. And so now I can use the product rule to combine this into one log. So it's very similar to the one that I just did. And let's go ahead and change to exponential form. So it'll be 3 to the 1st power equals x plus 3 times x plus 5. I'm going to go ahead and FOIL this off to the left. And so we're going to end up with 3 is equal to x squared plus 8x plus 15. So again, this is quadratic, so I want to get 0 on one side. So I just subtracted 3 on both sides. And I need two numbers that multiply to 12 and add up to 8. 2 and 6 are the numbers that work. And so we're going to end up getting -2 and -6 here. But I want you to notice if I plug in -6, -6 plus 3 would be -3, and I'd be taking the log of a negative. So -6 isn't going to work. -2 actually does. I'm just going to let you, if you want to check that, you can check it, but I'm going to leave it as it. I'm just going to tell you that it works because I just don't have enough time. I've already gotten to my 4th video in this review here. Let's look at P. So P, we're going to need to use the quotient rule because we have a subtraction of 2 logs. And again, I need to get that log, I need to just get a single log on the left here. So using the quotient rule, I get the log of 2x over x minus 3. Now again, notice our base is 10. So let's change this to exponential form. 10 to the first power equals 2x over x minus 3. So I'm going to rewrite that without the 1, and let's clear fractions by multiplying by x minus 3 on both sides. So on the right, we're going to get 2x. And notice on the left, we're going to have to distribute. We'll get 10x minus 30. Let's go ahead and subtract 10x on each side. We're going to get -30 equals -8x. Let's divide by -8. And so we get 15 over 4. And you can check that, but it does work. But certainly you're not taking the log of a negative if you plug in 15/4, because 15/4 is bigger than 3, so when you subtract 3, that'll be okay. Let's go ahead and look at Q. So notice, again, on the left side, we can use the product rule. I'm going to go ahead and do that. So this is the first problem we've had where we have log equals log, and they're both base 2. So if you have 2 base 2 logs that are equal, then these inner parts must be equal. I say equal parts. In other words, let's set these equal, because the only way these 2 logs could be equal, since they're both base 2 logs, is if these inner parts are equal. So x squared minus 3x, I just distributed there, is equal to 10. Let's go ahead and get 0 on one side, and the numbers that work here are going to be 2 and -5. So I'm going to go ahead and put the factored form there. And so you get -2 and 5. And notice if you plug in -2, that's definitely a problem here. Again, you can verify that the 5 does work. Alright, let's look at R. Alright, so again, we can use, well, on this one here, we're going to use the quotient rule. We have a subtraction of 2 logs. And so again, they're both natural logs. So our base is e, and so if you have 2 logs that are equal, like we do here, log equals log, the inner parts must be equal. So let's set our equal parts equal. I need to clear fractions. I'm going to go ahead and multiply the left side there, and I get 5x. On the right side, you got to distribute. You get 8x minus 4. Let's go ahead and subtract 8x on both sides and divide by -3. And so we get 4/3. And that is a good answer. You can check it if you'd like, but you're certainly not taking the log of a negative. That's the main thing to watch out for. Let's go ahead and move on. Alright, so it says a sum of $4,000 is invested at an annual interest rate of 5.9%. Find the account balance after 5 years if if interest is compounded, for A it'll be quarterly. So notice the 4,000. Well, first of all, let me write our formulas down. This is our formula for compounded interest when the interest is applied n times per year. And then we have the Pert formula, which is for continuous interest. So for quarterly, we're going to be using the first one here, but notice the 4,000, that's going to be our principal. The interest rate, we're going to write that as a decimal, 0.059. Our time is 5 years. And for A, it's compounded quarterly, which means 4 times a year the interest is applied to the account, and so n is 4. So I'm going to go ahead and write down the formula for this case, and let's plug in our numbers. So the principal we said was 4,000. It'll be 1 plus our interest rate, 0.059, divided by 4, the number of times per year the interest is compounded, and then nt, that's going to be 4 times 5. And when you put that into your calculator, just be careful that you either use 20 or just put 4 times 5 in parentheses, and you should end up with 5,360.94. So for part B, the only thing that changes is now this is monthly, and so n is 12. So same formula, but we're going to plug in 12 for n. And when you do that, you should get $5,368.62. When you get to C, notice the interest is compounded continuously. That's when we use the Pert formula, or what I call the Pert formula. So let's go ahead and plug in our numbers here. And when you plug that into your calculator, you should get $5,372.51. So don't forget, when you put an E in your calculator, just use second ln. And you may, depending on the calculator you have, you may have to put this part in parentheses. Alright, let's look at number 14. So here P is 6,000. It's going to be for 4 years. And in our first case, it's compounded quarterly at 8.25%. So we're going to be using the first formula. So let's go ahead and plug in the numbers here. Notice 0.0825 is our decimal form of 8.25%. And so on this one here, you should get $8,317.84. And let's see. On the second case here, now we're getting 8.3% compounded semi-annually. That means twice a year. So twice a year the interest is applied to the account. So again, we're using the first formula, and I'm going to go ahead and plug in the numbers here. And so when you put that into your calculator, you should get $8,306.64. And notice the last case here is compounded continuously at 8.15%. So we are going to use the Pert formula here. So you should plug in the numbers just like I did here, and you get $8,312.49. And so it looks like the best investment would be the first one here. Alright, and that's going to be the end of this video, and then we'll have one last one.